Hey everybody, in this video we are going to graph with transformation. Specifically, we are graphing the reciprocal function or a reciprocal equation here. Up top of my head, I have it written out with A, B, H, K. H shifting it left and right, K moving it up and down. A providing details of any vertical reflection, stretches, or compressions, and B providing any details about your horizontal reflection, stretches, or compressions. All of this stuff can kind of be tweaked and looked at sort of differently depending on how you choose to set up your equation. I'm not going to get too into it in this video. We're just going to do basic fundamentals. I'm going to show you a super helpful trick in getting points without making a table of values, plugging in numbers, to just bing bang boom, get it down on paper and graphed and finished and ready to go. So let's begin, shall we? To start, 1 over x, we have a restriction. The denominator of a fraction can never equal 0. That being said, 1 over x here, we have a vertical asymptote at 0 because x cannot equal 0. X cannot equal 0. That denominator x cannot equal 0. So vertical asymptote is at x equals 0. All right, so that asymptote acts like caution tape. It's like beep, 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 cannot go here, not allowed. End behavior is what gives you what we call a horizontal asymptote. They're both called asymptotes. One is very strict, the vertical, you can never, ever cross it. The horizontal asymptote is more truly end behavior. You can cross it in the middle. It's more about what is the trend of what's happening to this graph way out on either end. To find end behavior, we can use limit notation and a limit concept. The limit is asking about your output or your y value. This one is saying, what is the limit as x approaches, because you can't always get to whatever we're approaching, as x approaches negative infinity. So if I fill in smaller and smaller in the negative number sense, numbers for x, 1 over 10, 1 over 100, 1 over 1,000, but negative, right? So 1 over negative 10, 1 over negative 100, 1 over negative 1,000, what value is the fraction as a whole approaching? And the answer to that question is 0. It's getting closer and closer to 0. So out here on this end of the graph, we're getting closer and closer to 0. On the right, it's not always the same on both sides as we saw in exponential equations. As we plug in bigger and bigger numbers, 1/10, 1 over 100, 1 over 1,000, that one is also 0 coincidentally. So 0. So we have a horizontal asymptote, but 99.999% of times, obviously a made up statistic, but almost all of the time you will see it drawn completely through for simplicity purposes. Okay, next, if I, for argument's sake, for the first one, just I'm going to plug in a couple points to get the ball rolling. If I fill in 0, obviously I get undefined. If I fill in 1 for x, I get 1. If I fill in -1 for x, I get -1 for y. If I fill in 2 for x, I get a half. If I fill in a half for x, I get 2. If I fill in those same numbers but negative, it works out in that corresponding way. So what happens is you have this thing, which I'm going to call a branch, getting closer and closer to both asymptotes in that quadrant, and the same concept happening here. And there we go. We have 2 branches, quadrant 1 and quadrant 3, essentially. 2 branches going on right there. The domain, the x values that we use are from negative infinity until 0, and then right after 0 until infinity. The way we write that domain is, I feel like I'm not going to fit it there, but I'm going to write it here. So a little on a slant. Negative, am I on the screen? Negative infinity, comma, 0, 0's not included, a U symbol, but not like a real U with a tail, but a horseshoe look. And that means union. We're uniting 2 chunks of domain together. And then 0 until infinity is where we go. No bracket because 0 is not included, and that is our domain. The range is actually identical in this case because it goes from bottom to top, and it covers the exact same values. Negative infinity, comma, 0, parenthesis, that union symbol, parenthesis again, 0, comma, positive infinity. And please keep in mind, domain and range always go from smallest to largest. If you have ever in your parenthesis or in corresponding neighboring parentheses a value that is larger to one of the ones to the right of it, then something's wrong. That makes no sense. Okie dokie. Horizontal asymptote I could have written is horizontal lines always start with y. It's y equals 0. So what does this tell us? Fun thought. The y equals 0 is the equation of the x-axis. X equals 0 is the equation of the y-axis. Okay? Just to continue with the concept of limits for another moment here, the limit as x approaches 0 from the left, that's how you read that, of 1 over x. So as we approach 0 from the left, where are we going? In y values, we are going toward negative infinity. Negative infinity. And as we approach 0 from the right of this graph, where are we going? Positive infinity. They're always going to be going in different directions when the x in the denominator that gave you that asymptote is to an odd power. When the x in that denominator is raised to an even power, those limits as we approach from either side will both be approaching the same value of infinity, either positive or negative. To be continued in the how to graph rational functions. So if you want that explained, find any of my videos. I'll be adding them to this playlist, but find any of them on my other graphing playlist on how to graph rational functions, and I should go into it there. It's sort of like polynomial rules. All right, boom, that's the end of it. I spent way too long, 6 minutes talking about that, so we're gonna fly through this. Now, before I graph this one, what do I have going on? I have no shifting, no left, right, no up, down. I have a negative that's going to be a vertical reflection. So this branch here will be down here, and this branch here will be up there. And then I have a 4, which is actually a vertical stretch by a factor of 4. So what does that mean? This point will be 4 times higher off of this axis. So instead of over 1, up 1, it's over 1 and up 4. This point, which was over 2, up a half, will be 4 times higher. So it's going to be over 2 up. What's 1/2 times 4? 2. Up 2. That's a lot for some people to keep track of, especially when the numbers get annoying. So what is my magic secret trick? If we are just considering, for now, the portion y equals a over x, therefore, the 3 dots in a triangle mean therefore, if I multiply both sides by x, I get that a equals x times y. What do we know about x, y? X and y are the coordinates, the values that go into the coordinates of an ordered pair. The trick is, whatever numbers multiply to give you your top number, a, can be used from your new origin to plot points to make your branches. Allow me to demonstrate. Okay. Where are my asymptotes going to be? They're in the same place. So I'm going to use the same color markers. So I have a vertical asymptote because x still can't equal 0. I have the vertical asymptote here, and my end behavior is going to be the same thing. That's also not moved anywhere. So I'm going to draw in blue my horizontal asymptote right there. We had a vertical reflection and a vertical stretch of 4. Okay, and it's a little bright. So what multiplies to give you 4? How about 1, or even more specifically, negative 4? How about 1 times negative 4? 1 negative 4 from my center there, my cross of my asymptotes right there. How about 2 times negative 2? And how about 4 times negative 1? What about if I reversed it? What about negative 1 times 4? How about negative 2 times 2? How about negative 4 times 1? Now, without thinking too hard, I have nice points to draw my branches. I don't have to sit here and make a table of values where I can mess up. Easy peasy, lemon squeezy. There we go. They should be curved, rounded. Nothing should be pointy. I know this one's not my best drawing. Okay, and there you go. Amazing, beautiful. We love it so much. Let's do another one. Okay, here we are shifting this time. We are going to the left 8. We are going up 3, and we have a vertical stretch of 6. So let's go. Left 8, 1, 2, 3, 4, 5, 6, 7, 8. Up 3. This one's too thin. Okay, there we are. vertical stretch of 6. So let's use my magic trick. What multiplies to give us positive 6? And we're going to move there from my crisscross right there. So what about 1 times 6? What about 2 times 3? What about 3 times 2? What about 6 times 1? Could you do more? Of course. What about 1.5 times 4? Yada yada. What about 12 times 1/2? Boom. And then what about 2 negatives? 2 negatives multiply to give you a positive, right? 2, 4, 6, 1. So negative 6, negative 1. Negative 3, negative 2, negative 2, negative 3, negative 1, and negative 6. Now again, these are rational functions, of course, but these are rational functions in transformation form, or I guess some people might think of it as vertex form, but there's obviously not a vertex on any of these graphs. So we can graph them using transformations. Use the form it's in to your benefit. If it's not, if it's one of those crazy ones, you've got to go check a rational function video. Like I said, I definitely have some uploaded already, and I will be uploading more later. Here, last one, I'm already going a little long, sorry. For this one, where are we going? I'll actually color code a little bit more on this one. So we are moving right 5. 1, 2, 3, 4, 5. Down 1. Okay, and now the 12 is a vertical reflection and vertical stretch of 12. Now, I like a number like 12, 6, 4, anything that has a lot of pairs of numbers that multiply to give you that number, because it gives you more to work with, you know? So it reflected, so the branches are here and here. So what multiplies to give you negative 12? How about, I don't know if I can fit 12 on here. 2, 4, 6, 8, not really. So I'll start with 6 and 2. So positive 6, 2, 4, 6, and negative 2. What else can I do? I could do 4 and negative 3. I could do 3 and negative 4. I could do 2 and negative 6. There's a branch. And then 2, negative 2, and positive 6. Negative 3 and positive 4. Negative 4 and positive 3. And then that's 4, 5, 6. Negative 6, positive 2. And that's how you can draw a really precise graph. Now you might be thinking, why do I need a precise graph? I don't care. My teacher just lets me bloop, bloop, bloop and draw little things. If you plan on taking calculus in the future, one of the things that you're going to be doing is finding area between functions, or finding the volume of a solid of revolution. In order to do that, you need to set up the bounds for your integration, and you need to know your lower bound and your upper bound, or your left and right most extreme values. So you need to know where they cross. You need to know which graph is on top and which graph is on bottom, or you need to know which graph is further left and further right. You need to understand how graph works. The whole beginning of calculus is limits, and limits are applied to functions. So if you don't have a concept of what they look like, limits are a lot harder to think of in purely an algebraic sense as opposed to a visual graphical sense, and it becomes a lot easier. Thumbs up if you think you could transform the reciprocal function 1 over x. Questions, comments, concerns, put it in the comment section. Answer somebody else. Answer your own question. I'll answer your question. I don't know what to tell you. Next one will be 1 over x squared, reciprocal of x squared, or the volcano. And already did linear, absolute value, quadratic, cubic, square root, cube root, exponential, and logarithmic. Sayonara.